Alrighty, howdy everybody. Hi, I'm Remy, as you can see from the slide and from some people calling out about it. We are here to take a look at how to build a synthesizer, a musical instrument, in roughly about 5 lines of your own code. As said, I'm Remy. By day, I am a creative coder at a company called Ion Tank. We do some installations. There's some people here that do that. We do some kind of artistic pieces. I mostly write software that makes LEDs blink pretty. I am an amateur violinist. Amateur is a fancy way of saying not very good. But I like music, I like playing music, and most important for this talk, I am an extremely lazy person. And I want to do absolutely as little work as I can get away with to accomplish a goal. And this is going to be really, really relevant. You can see my Twitter, my GitHub. I'll have these on the slides at the end as well. Feel free to look them up. All of the code, everything we're going to play with in this session is going to be up on that GitHub. You'll be able to find it there. In addition to playing with synthesizers, this is also a lesson in false advertising, because I didn't actually count how many lines of code there are in this session. There's actually going to be a lot more than 5. But I can tell you this, despite the fact that this is going to be probably one of the more code-heavy talks you're going to see, we're going to look at a lot of code, it's going to be a lot of really, really simple code. It's the sort of code that is so simple, you don't even really need like a unit test. It's one line out of a library, and it's going to be super duper simple code. You could do this in less than 5 lines of code, wouldn't be as interesting. And you know what? Counting lines of code is kind of a waste of everybody's time. It doesn't matter how much code you write, it matters what the code does. But, so I don't get in trouble for lying, this is exactly 5 lines of code. This does audio synthesis. So we have a 5-line synthesizer. I didn't lie to you at all, okay? The one thing I do want to note here, though, on this, these are the 2 libraries we're going to play with. We're going to do all this in Python, and we're going to use 2 and only 2 libraries for this whole thing. We are going to use NumPy, which is numeric Python. We're going to talk a little bit about what that does. We're also going to use this sound device thing. We're not going to talk about that because I don't care how it works. It just plays audio, and that's all I care about. It can play audio. It's its only job. So we're going to talk a little bit about music. We're going to talk about something very, very important. We're going to talk about time. We're going to use what are essentially trivial amounts of Python code. I actually started this as a weekend project because I was bored, and I found myself in a position where I'm like, it can't be this easy. What I'm doing can't work this well. It can't be this simple. I'm doing something wrong. So we're going to have some trivial amounts of Python code. We're going to talk about NumPy a little bit. We are going to make a lot of little bleeps and bloops. That's the most important thing. And really, we are going to try and use our intuition about how code should work, about how this software should work, about how this library should work, to find a way to get to some really interesting results. We're going to start with some really, really simple code, and we are going to get very, very complex output as a result of this. And as I said, we're going to do this super simple. It's almost entirely one-line functions. There are a few longer ones in there, but we're not going to talk about them very much. Most of this code is so simple that you'd be wasting your time unit testing it because you'd just be unit testing a pre-built library. We want to build a synthesizer, which means we want to make music. What is music? There was a talk on Wednesday about machine learning for generating music, and they asked the exact same question. And they got to some of the same sorts of answers. We often think about things like notes and beats and rhythms and patterns and so on. That's a smart way of thinking about music. There's a lot of structure to that, and there's a lot of information in that. But some of my actual experience goes in slightly different directions. For example, I used to play music with a guy who played a modular synthesizer. Little box. Each module in the box does some piece of audio synthesis, and depending on how you wire it up, it's going to be a different instrument. The actual structure of the music is constructed in the device. And that was a really interesting way to think about it. It's not a way I had thought about music previously. And around that time, I was also doing a little research and learned a lot about Beebe and Louis Barron. You probably may have heard of them. They did this most famously, the soundtrack for the movie Forbidden Planet. Great movie, amazing soundtrack. A soundtrack where they wanted to make music that sounded truly, truly alien. and they turned to electronic music to do that, and they had a really interesting approach to doing this. They would build an electronic circuit, and they would not have a clear idea of what that electronic circuit did. They had an intuition about it. You might notice a theme here. They had an intuition about how that was going to work, but they didn't know how it was going to work till they recorded its output. And they would often run them to destruction. They thought about it as the life cycle of an organism. And they would record this entire life cycle till the circuit burned out, and they take the tape and cut it up and collage it into their final composition. And when we think about things like modular synthesizers, and we think about this approach of analog circuits, we can think about music in a completely abstract way. Music is nothing more than a signal that varies with time. We look for other things. As human beings, we look for other things that make it music, but really, it's just a signal that varies with time. Now, time is hard to work with a computer, right? Because time is a continuous value. You can take any unit of time and subdivide it into infinitely more subunits of time. It is a continuous value. But when I say that out loud, I think to myself, I've heard the word sampling before. Now, I don't need to know exactly what sampling is. I don't need to know how it works. I don't need to know about Nyquist sampling theorems or Shannon entropy or any of that. All I need to know is that I can sample time somehow. I can take a continuous value and sample it. And as it turns out, our very first NumPy function that I want to talk about is this simple linspace function. Short for linear space, which is a really fancy way of saying I count. I count from 0 to 1, and I'm going to take 44,100 steps to do it. Why did I pick that number? You know, I happened to see it in a piece of audio software once. It probably is important that that number is that number. There might be some other numbers that are slightly better. I don't care. All I need to know is that I can count from 0 to 1, 44,100 steps. And so here we go, goes from 0 and a lot of small values all the way up to 1. We've just created time. I'm going to actually, this seems useful, so I'm going to save that as a function. Here's our first one-line function. Very, very simple. I'll make that sample rate thing configurable because, again, it sounded important. I don't really know what it does or why it matters, but it seems important. So I'm going to keep that high number there. And so I can go ahead, I'll call that function space1 here. I'm going to get 1 second of time. And then I'm going to bend time to my will and create something amazing. But before we get there, we have to count. So here's a lovely graph that shows us what time looks like. It's a line that goes in one direction. But I need to do something with time, and I know, again, music's a time-varying signal, so I need some sort of wave, right? And because I remember a little bit about high school, I remember sine waves. So I need to take time, and I need to turn time into a sine wave. And I'm going to pick my favorite note, the concert A, 440 hertz. If you play violin and you're good at violin, you're the concert master, and you get to play the concert A as a single note to tune the whole orchestra up. It's very powerful. I would love to experience it someday. But 440 hertz is 440 cycles per second. 440 cycles per second would be a sweep from an angle of 0 radians to 2 pi radians because circles and sine waves are related. Thank you, Wikipedia. So I'm going to do that. I'm going to take time. And I know that time times 2 pi times 440 means in 1 second of time, I'm 440 times going to cycle through 2 times pi. And I get this lovely wave as an output. And what do you know? When I play it, I get a lovely, perfect tone, perfect pitch. That seems useful, so I'm going to save that as a function too. Notice here I'm going to add in a little shift value there, because we can shift the phase of the wave where it starts. Seems important again. Might have a use for that later. What I just did here was take advantage of some of NumPy's really, really important features. In fact, let me skip here. This right here is the big idea. Because we can take a NumPy array. Numeric Python is a tool for managing large sets of data in Python, and we can take an array from NumPy, pass it to functions, we can add them together, we can subtract them from each other. So here's a version where I do my linspace, right, from 0 to 2 times NPy in 5 steps, in 10 steps, in 1,000 steps. Right? I can take an array, pass it to the sign function works on arrays. This is the most important thing. From a technical standpoint, this is the only thing you really need to take away from this. There are other things that I hope you take away from this, but from a technical side, this is the only thing that actually matters. NumPy arrays can go to functions, they can go to arithmetic operations, and this allows us to write some really simple code. So, in fact, let's look at this. Here's an array. Here's an array. I'm going to do some math on arrays, and what do you know, it works, right? I take the first array, multiply it by 2 times pi, and boom, I get my values there. I take my second array, and I add it to the first array, right? A plus b. Wow, exciting, right? We can do arithmetic. Wait, we can do arithmetic. Well, what happens if I take one sine wave, another sine wave, a third sine wave, and add them together? The fancy word is constructive and destructive interference. The practical word is I've made a chord. And so I have this much fancier sort of sine wave here. It's almost musical. Almost. We're not quite there yet. Now, one thing, it didn't come out super ugly in this version. When I was initially doing this, I was doing it on Linux. Pulse Audio will clip that because you've gone outside of the range of -1 to 1. Doesn't like it when you do that. And you know what? For making the math simple, I don't like it when I do that. So we're going to just divide by 3. It's the same sound. It was a little cleaner. It's the same wave, just notice I'm scaling it between 1 and -1. Makes the math simpler. So we just added, we just signed, we did a little division there. There's one operation that we remember from grade school that we haven't done yet, haven't multiplied. And that gives me another idea. I'm going to make a slightly longer period of... Boy, this laser pointer does not like me. Oh, it helps if you hit the laser button. I'm going to make 4 seconds of time, and we're going to bend 4 seconds rule. We've mastered this 1 second thing. I'm going to create my 440 hertz sine wave again, but then I'm going to create a 1 hertz sine wave, 1 time per second. And so you can see, here's the whole 1 time per second sine wave, right? 4 peaks, 4 valleys. We do that 4 times per second. And if I multiply them together, when the 1 hertz wave goes down towards 0, the whole value goes down towards 0, because when you multiply things by 0, turns out they go to 0. Which means, all right, so we have now this ability to kind of gate our sound. Simple arithmetic, simple multiply, divide, we now have a gate, and I can now combine this with my chord. Here I'm going to have my C, my E, and I'm going to have them all go at slightly different rates, right? Here's my A with a 1 gate wave. There's my C with a 2nd gate wave at a different rate. There's my E with a different gate wave at a different rate. And when I play this, it's kind of like cosmic. All right. And I get a nice little pattern you can see. It's always nice to see pictures of sound. Feels fancy. So we can do sine. Sine is great. Sine is easy. There are a lot of other types of waves. We're not going to necessarily see all of them. But a really good one would be square, right? Because a square wave is a sine wave. It's just really extreme, right? You're only high, you're only low, you're never in between. Sounds like my life. And as it turns out, NumPy gives us a function for this. If I pass an array to the sine function, not to be confused with the sine function, it's going to give me a -1 or a +1, depending on whether the value I gave it is positive or negative. Which means if I plot a sine wave through the sine function, yeah, it's not confusing at all, I'm going to get a lovely little square wave. Square waves are cool. They sound a little different. Boy, that was a long 4 seconds, wasn't it? Going to save that as a function. Seems like it'll be useful later. Notice I'm just using my sine and my sine. And I can combine this with my gate. I can still do that multiplication. 3, 4, 5, 6, 7, 8. And I can even plot out. We can see there's the square wave, and it's being shaped by that low frequency sine wave. Nice little pulses. And you know, if we're going to have a square wave, we can do some beats with a square wave, right? It's high, it's low. I can constrain that in order to control the behavior, right? Multiply by 0, you get 0. So I can use these to make beats. I just need a function that's going to keep my square wave not -1 to 1, but 0 to 1. Which, hey, what do you know? NumPy gives us a function for that too. This heaviside, honestly, I don't even know how you pronounce that. It's a statistical thing. I don't actually know what it's really for. But for me, I'm going to pass it an array, and I'm going to pass it the value 0. Everything less than or equal to 0 is 0 out of this function. Everything else is going to be 1. So you can see here I passed a set of values, and there's my output. Everything 0 or less turns into 0. Everything else turns into 1. So now I can take my square wave, I can heaviside it, and so I'm going to have a 2 hertz sine wave, which happens to be 120 beats per minute. Which gives me a square wave that looks like every other square wave we've seen. But when I multiply things together, we're about at a techno song. All right. We can get wacky with this. I'm going to try an experiment because I'm feeling really confident at this point. I've played with a few of these things. They worked the way my intuition said they were supposed to work. And so with that in mind, I'm going to create a sine wave. I'm going to give it a pretty low frequency. It's only 10 hertz, right? Very low frequency. And I'm not going to scale it 0 to 1 or -1 to 1. I'm going to multiply it by 5, so it's a big range. And then I'm going to create another sine wave, and I'm going to take a frequency, 440 again, and I'm going to take this other sine wave, and I'm going to add them together. I don't really know what this is going to do. If I graph it out, it doesn't look very interesting. It looks like a sine wave. Something's going on though, right? This seems interesting. The UFO has landed. Okay. So I can take an array and pass it as my frequency. And that makes sense, right? With everything we've said so far, frequency times space is what we've been doing, right? We've been multiplying our time by our frequency, by pi, and we know that we can multiply arrays together. So if my frequency is an array and time is an array, then that's allowed. So my frequency can change with time. Oh. Wow, it makes me feel kind of smart to figure that out on my own. And that gives me another idea. Because what I can do here is I can create another array, and I gave it the wonderful name buffer. This is a great name for an array, right? Should always do this. And I'm going to fill the whole thing with 440. You know what, not the whole thing. I'm going to fill the second 2/3 with a different frequency. You know, not the second 2/3, because the last third is going to get a different frequency. And if I graph this out, we have a lovely little staircase, 440 to 523 to 659, and oh, that's a song, sort of. I mean, it's an arpeggio. Let's combine that with our gate. Let's try and make it something a little more musical. There's something there. It's not my favorite song, but it's got a beat. You can dance to it. All right, so with basic arithmetic and a few functions that we stole from a library, we can do audio synthesis. And we don't have to know exactly what we're doing here. We can just sort of fumble around, feel our way through, experiment a little bit, and we'll get all sorts of weird results. Some of them weirder than others, some of them good, some of them bad. Spoilers, I only gave you the good ones, at least kind of good ones. There were a lot of bad ones along the way. But there's more, right? We've got this very, very simple synthesizer built out of very simple techniques. And so now the question becomes, are there other things we can do with this? Well, what about some other waveforms? Really got to hit the laser button, not the slide advance button. Do we care about normalizing? I talked about that -1 to 1. What about building an actual song? Can we make an actual song? Spoilers, we're going to make about a 13-second long song. There's only so much time for this presentation. But other waveforms. One of the big ones that you often hear about when you hear about synthesis is a sawtooth wave. I do not know the math that you need to define a sawtooth wave, but Stack Overflow does. So I copied, pasted, and did a little revision in order to make that work. I mean, it makes sense, the thing about the tangent and the arctangent, right? You got that sort of shape on a sawtooth. What sort of shape on a sawtooth? That sort of shape on a sawtooth, right? Okay, so I can have this handy-dandy little function, right? Create a utility function to generate saw waves. A little buzzier, a little different tone. Super simple. Again, this is our longest function so far, right? And it's 4 or 5 lines, but really it's like 2 lines that actually count and a lot of white space so that you can read it. Here, let's get really complex. Square waves are cool, but pulses are cooler. Because pulses let you change the duty cycle. How much time do you spend high versus how much time do you spend low? A square wave spends the same amount of time each way, right? Well, a pulse lets you set the duty cycle. He said duty. A pulse lets you set a duty cycle. And what do we do to do this? Well, I'm going to make 2 square waves, and I'm going to shift one of them over a little bit. Then I'm going to take the difference between the 2 square waves and chop it off. And I might do a little extra math if I want it to be a sound versus a gate, because I might use this for a couple different purposes. We don't care about that. This is the longest function I'm going to show you today. Pretty simple function even still, right? We take a square wave, find the difference between the 2, shelf them off at 0, and then return that wave, maybe with a little modification. This allows us to generate a couple of different duty cycles. Duty cycle 25%, 12%, 50%. These sorts of things allow us to get the same pitch, but with different, as the musicians say, overtones, right? It's the same frequency here. Here's a 50% wave. It's the same square wave. And it's the same square wave. We've heard that sound before. But what about the 25% duty cycle? Same frequency, but it sounds different, right? Getting into a little more of a Nintendo-y sort of vibe there. Or 25%. That was the 25%. Shouldn't put the graph after. Oh well. Here's a 12% duty cycle, so much sharper peaks. And again, slightly different tones, slightly different sound, different overtones. We also do want to be able to scale this. That's basically just some simple math though, right? If I know that I've added 3 signals together, then I should divide by 3 because I want to make sure when they constructively interfere, right, I'm chopping off the peaks. There are also functions that I can use to find the maximum value and then just scale according to that. We can get clever with scaling, but I'm not going to worry about that for this, right? We've only got so much time for this talk. I'm not going to worry about it here. The other function I want to take a peek at though, and this is actually one of my favorite functions, and yes, I am the sort of person that has a favorite function. I'm also the sort of person who wore Tesla socks today, so I am that person. But my absolute favorite function is a function known as Smoothstep. And I encountered this because I do a lot of graphics programming, and this is an OpenGL function, and I just stole the implementation from OpenGL here and made a NumPy version of it. This is known as a Hermite interpolation. I don't know who Herm was. But it's a really useful function for a bunch of different things. It's actually used in machine learning. So if anybody did go to any of the machine learning talks, when they talk about some of their backpropagation functions and error functions, they often will use a Hermite function to do that. Also known as a sigmoid function. But there's some math here. Again, I didn't make up this math. I don't actually know how this math works, but I know what this math does. It makes this lovely little S-shaped function. This S-shaped function is great. It's great for audio. We'll see how in a second. It's great for animation. It's great for drawing things. I use this function all the time. And so what I can now do is I'm going to make a smooth step from 1 second to 1.5 seconds. So I'm going to have an S-shaped curve made out of time, and I'm going to multiply a note by that curve. Got a nice little fade in there, didn't we? Took about half a second to go from nothing to a full frequency. All right, play that again. 1, 1,000, 2, 1,000. And now I can combine all of these. Remember our same notes as before, but I'm going to now make gates for them. A is going to go from 0 to 1, then C from 1 to 2, then E from 2 to 3. Practically conducting here. All right, fantastic. And all I'm doing here, right, is outputting one of these sigmoid curves, right? Here, my axis is the amount of time that's elapsed down here. So you can see, starting at 1 second, this gate starts fading in, and it reaches full intensity around 2-ish seconds. And if I can add those gates together, I should be able to subtract them too. So here I have a gate that starts there, and gets subtracted from that one, and I'm adding another one. It's a long block of code. It doesn't all fit on the slide, but it doesn't matter because we know what Smoothstep does, so what happens when we add and subtract them. Get notes to come in and out and fade in and out. And if I plot just one of those, this A gate here, you can see, right? Fades in, fades out, fades back in, fades out. We are composing with signals. And since that seems like a useful function, I'm actually going to make a waveform out of it. This will be handy in a second. We're just going to take Smoothstep and a sine wave, and we're going to combine these together. And that's going to actually allow us to get this weird, funky little curve. It's a sine wave with a shelf. It's kind of cool. Sounds weird. I'm sorry? Distorted. Yeah, it's a little distorted bit of a wave there. And with all of these tools, and a few that I'm going to kind of hand wave a little bit, we now have everything we need to compose a super short song, right? I have a lovely little library called Shaded. If you're very, very clever, you might recognize that I named this library this because of my inspiration from OpenGL shaders. This is actually kind of a musical shader. If you've ever done any graphics programming, that might sound interesting. And what I'm going to do is I'm going to create a 13-second long block of time. That is my song. I'm going to give us 13 seconds of time. And I'm going to use that Smoothstep function to give my song an overall envelope, right? Because I know music doesn't just come in really loud. It comes in, and then it goes out a little bit. So that's what I'm going to do. I'm going to have a little curve here so that my song comes up pretty quick, gets its full intensity, and then fades out by the end. And now I want to start combining a few other things together. Remember how I had that little step of notes, right? Where I could cycle through 3 different notes, made that little staircase. This ARP function automates that a little bit. So I just built that. It's the same thing. But what I'm going to do is I'm going to take this sequence of notes, and you can see I wasn't sure which pitch I wanted them to be at, so I started at 1, and I realized that was too deep, and it sounds really bad when I play it through these speakers. So I multiplied by 2 to make it a little higher pitch. This time when I'm multiplying, this list here, by the way, is just a Python list, so it's not actually a NumPy array. So this multiplication doesn't say multiply by 5, it says repeat this 5 times. So this is a sequence of notes that's going to be my baseline 5 times. Do, 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 do. That's not what it sounds like, I just can't sing. And then I'm going to go ahead, I'm going to do a little sine wave of that song, and I'm going to put a little beat to it. I'm going to use that pulse, that duty cycle pulse, to give myself a little bit of a beat, and okay, I'm just going to go ahead and move on because we got other stuff to see. little spy hunter sort of thing going on. I have a little noise function. Noise is what you'd expect. It takes time and just makes random output in time. Good for drums. So I'm going to go ahead and output a little noise. I'm going to use that sigmoid function. I'm going to combine a couple of sigmoids together in order to give myself a sort of funky little drum beat there. This is what that set of gates kind of looks like a little bit. Just a little sample of what's in there. So we got a little bit of a rhythm. When I combine it with the actual white noise, this is what it looks like. So we have a nice little set of peaks and valleys there. I need some sort of melody. So I'm going to use that ARP function again. I'm going to output some notes. We'll have a couple lines in our melody. Combine them together. We're going to use that saw wave here because it sounds a little string-ish. And then we're going to put the whole thing together. It's not the greatest song. It's okay. You don't have to act like I composed something really great. But when you look at this, it's a little hard to understand what this big block of code here is doing. There's a lot going on. But what I want you to really concentrate on is how small each of those individual steps were, right? Every single function I showed you was essentially a single line of code. Every operation we did on the output of those functions was basically add it, subtract it, multiply it, divide it, or hand it off to another function. And that really lets us do very complicated things with very simple code, which is one of my favorite experiences to have because I hate doing complicated things. It feels like a lot of work. And as we established at the top, I am lazy. In fact, I'm so lazy, I decided that the easiest way to do my slides was to write a stylish browser extension to hide the parts of my notebook I didn't want you to see at the time. That's the level of laziness I'm at. Each piece of our code is super, super simple, but we get complex behavior. And as we go through, we don't need to know what we're doing. One of my favorite parts of building this project is that at each individual step, I honestly didn't know what the output was going to be till I wrote the code, which is really fun. I don't need to worry about making it good. This is certainly not the best way to do audio synthesis. If you think about it, we're doing it all in memory for starters. That's kind of expensive. But it's a fun way to do it, and it's good enough. And one of the things that I think is really important, to quote someone or paraphrase someone, programming should make you happy. Working on this particular project really did make me happy. I had a lot of fun making this project. And that source is available, and I would really, really love to see other people's projects and hear the sorts of things other people do. I have a bunch of example code up there, including a much longer composition, which is also up on my SoundCloud. There's not much else on my SoundCloud, and none of it's actually very good, but that's fine. There are a lot of other places we can go with this as well. This is the sort of thing where we could add some features to maybe make it a little less bad. There's also a lot of other functions that we didn't talk about. NumPy has an fmod function for floating point modulus. What happens when you fmod a sine wave? I don't know, but I bet you it sounds cool. What happens if you reverse time? What happens if you flip bits of time around? These are all things you can do, and they're experiments that you can do with 1 or 2 lines of code, and then you immediately execute it and hear the result. And that's the most important part. The most important thing is getting yourself to the point where you can just go and run some code and get a result, and then iterate on it, and it is so much fun. So I want to thank everybody for coming. Hopefully everybody enjoyed. I'd love to hear some of your music. Thank you very much.